You might remember these plots from the previous videos. These are depictions of gravitational potential energy. In the first situation, we have a single star forming a gravity well. In that situation, the orbits of the planets were stable and circular. You might also remember that when a second star was added to the system, that the inner planets that were orbiting very close to their respective stars mostly remained in their original orbits, whereas those that were originally in higher orbits tended to start wandering around the entire two-star system rather than moving around just one star. In the case of many stars, we still had a situation where the lower orbits of any planet would be bound to their individual stars, but again, the outer planets might start meandering around the entire system. The point here is that an analogy exists between gravitation and electromagnetism, because the case of a single isolated atom, the electrons will occupy certain energy levels corresponding to their allowed orbits. But in the case of a crystal, where we have many atoms nearby one another, there is absolutely no reason to expect that the orbits will be the same. In fact, we have every reason to believe that the electron orbits will be disturbed when we put many atoms near one another in the case of a crystal. In fact, it's true that even in a crystal, those electrons which were originally very close to the atomic nuclei, in the case of an individual atom, will remain bound to their original atomic nuclei. They do largely stay in orbit. For those outer electrons, though, they may start moving around the crystal as a whole, and it's the ability of those electrons to move around that leads to electrical conductivity in solids. The potential energy landscapes seen by an individual electron depends on the surrounding environment. In the case of a hydrogen atom, for example, the only environment seen by that one electron is a single proton. However, in the case where we hypothetically bring another proton nearby, we would expect the allowable energy levels to be disturbed a little bit. And the closer the second proton approaches, the greater the amount of change. This is not the plot of H2 or gaseous hydrogen, by the way. This is just a toy model to illustrate a point. And that's the following. If we have two atomic nuclei a certain distance apart, then some of the electrons, particularly those which are in the lower orbits, will remain bound. But some of the electrons, particularly those that might be in the higher orbits, will then be able to move around the entire system. Because we have now, with two atoms, twice the number of electrons that we would have had before, we will have twice the number of possible energy levels as before. In the case of a crystal, there will always be some of the electrons which remain bound to their own nuclei, and then there will be some other electrons which are free to roam around the crystal as a whole. You can imagine the movement of electrons inside a solid as similar to the movement of water inside this bottle. If I have a bottle with just a little bit of water, and I give the water some energy, for example, by tilting the bottle to put one end of the bottle at a higher potential energy, then the water can easily flow from one side of the bottle to another. This is similar to the situation of applying a voltage to a piece of metal. It's very easy to get the free electrons in a piece of metal to move when you give them a little bit of energy. On the other hand, if the bottle were completely full of water, then we can't very easily get the water to move no matter how much we tilt it. The water just can't move from one side of the bottle to another. And this is almost just like the situation where there's no water in a bottle at all. This is like a piece of glass. No matter how much voltage I apply to a piece of glass, I can't get the electrons in it to flow. And it's not because a piece of glass doesn't have electrons. Glass is absolutely full of electrons. The problem is that those electrons in glass are not mobile. Let's now consider the situation in a piece of silicon. If you've taken a chemistry class before in high school or university, then you might have seen this notation here. This is the notation used to describe the orbits of electrons in an atom. If you've not seen it before, it's okay, because I'll explain it to you in the case of a silicon atom. So first, let's consider the energy levels in an isolated atom of silicon. The notation works like this. In the first lowest energy 1s orbit, there are 2 electrons. Energy is plotted vertically on this diagram. In the 2s orbit, there are also 2 electrons. In the 2p orbit, there are 6 electrons. In the 3s orbit, there are 2 electrons. And in the 3p orbit, there are 2 electrons. And it's worth pointing out that the 3p orbit is not completely full. There's room for 4 more electrons. In total, silicon, which has atomic number 14 on the periodic table, has 14 electrons, and there are 4 openings in its outermost orbit. Now let's consider the situation where we would have, hypothetically, 2 atoms of silicon near one another. Obviously, the outermost orbits might change the most. Because we have 2 atoms, we have twice the total number of electrons. In the 1s orbit, we now have 4 electrons, 2 orbiting each atomic nuclei. The 2s and 2p orbits also wouldn't change energy levels very much because these electrons are tightly bound to their own respective atomic nuclei. But the outermost orbits will certainly change energies, and the labels 3p and 3s start to lose their meanings because whereas in an isolated atom we had only 2 allowable orbits holding 4 electrons in total, we now have 2 completely different energy levels holding the electrons. But it shouldn't be surprising that the electron energy levels have changed. Certainly in the case of a crystal, we have 14 electrons per atom, so the number of total electrons is a gigantic number. There will be many more energy levels permissible in a crystal compared to the case of an isolated atom. And like the case in an individual atom, the lower energy levels will be full of electrons and the upper energy levels will be unoccupied. At some energies, there are no electrons. Just like in the case of a single silicon atom, no electron orbits between the 2p and the 3s orbit. In the case of a crystal, there might also be gaps in energy where no electrons are orbiting. Let's now draw in a few of the electrons. We have some electrons down here in these states which are densely filled. The electrons can't really move around the lattice at all because there's electrons all over the place. And this is just like the situation where the bottle is completely full of water. It's not easy to get any single molecule of water from one side of the bottle to the other when it's surrounded by too much other water. It turns out that there's an energy gap between the highest occupied energy level in silicon to the lowest unoccupied energy level of 1.17 electron volts. So the electrons are completely filling up all of these low energy states in a silicon crystal, and then there are a lot of unoccupied states up here, a distance of 1.7 electron volts away. If the electrons just had enough energy to get up there, then they would be free to roam around the crystal. But 1.17 electron volts is actually quite a lot of energy. So by and large, silicon is an insulator. There are a lot of unoccupied conduction states available here, but there are no electrons up there. That's like the situation in an empty bottle of water. There can't be conduction because nothing can move. But in the so-called valence states, they are completely full of electrons that have no room to move around. If we were to somehow supply silicon with electrons that are in this right up at the top, at this level, by somehow giving them the energy that they need for some of those valence electrons, for instance, then the electrons would gain enough energy to move around the crystal. Now it's worth taking a step back and reminding ourselves that this situation is different from the work function. Work function is the energy needed to get an electron completely out of the crystal altogether. This 1.17 electron volts is the energy needed for an electron to move from a lower confined orbit to a higher, more mobile one. In order for silicon to conduct electricity, we would have to impart 1.17 electron volts to its valence electrons in order to get enough of them up here into the conduction band. Only materials with free electrons can conduct electricity. And that's not the case in silicon, which is why silicon is a very good insulator. Of course, there's an easy way for electrons to be promoted from the valence band into the conduction band, a rather simple way, in fact, for those electrons to gain the 1.17 electron volts of energy each, and that's through heating. And if you take a silicon wafer and you measure its electrical conductivity at room temperature, and then you heat it up by 100 degrees and measure it again, naturally you'll find out that the silicon wafer is a lot more conductive at the higher temperature, because statistically you're always going to have a few electrons that somehow manage to gain enough energy thermally in order to be up there in the conduction band. And on the next slide, I have an approximation of how one might estimate the numbers. Now, this is an overly simplified equation, so the answers won't be quite right if you try to plug everything in, but it should give you a very good indication. This equation has not, for example, been corrected for quantum mechanics, so it's a very rough approximation. This is known as a Boltzmann distribution, and in the equation, N sub C means the number of electrons at the conduction energy level, and N sub V means the number of electrons at the valence energy level. So the number of conduction electrons versus the number of valence electrons is approximately an exponential function that's related to the size of the energy gap between the two levels and also to the temperature. K is the Boltzmann constant. And if you plug in numbers, you'll find that the ratio of these two numbers of electrons and levels, which are 1.17 electron volts apart, is absolutely tiny. It turns out that silicon has approximately 1.5 times 10 to the power of 10 electrons in the conduction band per cubic centimeter of material. Now, that might sound like a big number, and you might think, wow, silicon has 10 to the power 10 conduction electrons roaming around the crystal, but actually, this is not very many at all. Because there's something like 10 to the 23rd power of silicon atoms per cubic centimeter. So this means that only 1 out of every 10 to the power of 13 or so of the electrons in the crystal are actually conduction electrons. So this is why silicon is a very good insulator. So although this is a very big number, it's actually a really small number when you compare it to the total number of electrons in the silicon crystal itself. Heating up a piece of silicon will increase the number a bit because of the temperature in this equation. But the silicon will actually melt before enough electrons make it up to the conduction band in order for it to conduct electricity. However, if we look at the same number of conduction electrons in, say, germanium, you see that the numbers are higher because germanium at room temperature has more electrons floating around up there in the conduction band compared to silicon, and that's because it has a smaller energy band gap compared to silicon. So it's easier for a few of its valence electrons to be thermally excited up there at room temperature into the conduction band. If you heat it up, then T changes in the equation, and these numbers will change. But even germanium is still an insulator. By the way, when electrons in the valence band get promoted into the conduction band, say by heating or by light absorption, then they leave behind openings or holes in the valence band. And in fact, I've drawn one in this little diagram, although it might be a little bit hard to see. In any case, any electron in the conduction band is now free to move around the crystal, like water moving around a mostly empty bottle. But the hole in the valence band can actually move around too. And this is similar to the situation of a small bubble of air moving around in a bottle full of water. If I move the water around, the water might not move very much, but the little air bubble can move all over the place, right? That's a situation of a hole in the valence band. In this analogy, the water represents the negatively charged electrons, but the hole, or the air bubble, moves in the opposite direction to that of the water. So it behaves as if it's positively charged, and it makes sense because the absence of a negative charge in a sea of negative charges is a lot like a positive charge in its behavior. Now it's easier for electrons to move around in the conduction band than it is for these holes to move around in the valence band, because for a hole to move, a lot more electrons have to actually flow around the bubble. You might say that an electron is more mobile than a hole, or an electron has a higher mobility than a hole. So if I would ask the following question, silicon at room temperature contains 1.5 times 10 to the power of 10 conduction electrons per cubic centimeter. How many holes in the valence band does the piece of silicon have at room temperature? The answer is exactly the same number, right? Because every single one of those electrons in the conduction band started off in the valence band and moved to the conduction band through thermal excitation, leaving behind a hole. Now, silicon has a gap 1.16 electron volts. In an earlier video, I said that sodium chloride, or solid salt, is a very poor conductor of electricity. In fact, it's really difficult to make solid salt conduct electricity. Of course, it's a totally different story for molten salt, or salt, which has been dissolved in water. But solid salt is a really good insulator. Masodi et al. Have actually measured it out in a paper in 2014 and published the results in Physica Status Solid E. And this is the valence band in sodium chloride. The conduction band's way up here, 8 electron volts away. In the case of sodium fluoride salt, there's an even larger 12 electron volt gap. And you know why salt is transparent, don't you? Because if you try to hit salt with visible light, there's nowhere for the electron that absorbs the light to go. So it can't absorb the light. Salt is transparent. You need something deep in the ultraviolet range in order to promote a valence electron in sodium chloride into the conduction band. Let's compare several materials at all now on the same slide. All these 5 materials are insulators. They do not really conduct electricity. But it doesn't mean that the electrical conductivity is 0. It's just really small. So you'll always have a few thermally excited electrons in the conduction band for all of these materials. And it's true that germanium has a higher electrical conductivity than silicon. Silicon has a higher electrical conductivity than diamond. But thermal energy is not the only way to promote electrons from one energy level to another. We already know that absorption of light is another method through which electrons can gain energy. The first 3 materials here are transparent, but silicon and germanium are not. And this is because visible light has sufficient energy to promote the valence electrons in silicon and germanium up into the conduction band, but there's insufficient energy in visible light to promote valence electrons in diamond and the 2 salts here to the conduction band. Thus, visible light cannot be absorbed in these materials, and so they're transparent.